Hi guys, welcome back to Chemistry with Harshada. Why is vinegar sour and acidic, but alcohol isn't? The answer lies in a tug of war happening at the atomic level. It's called the inductive effect. If you understand this, you can predict the strength of almost any drug molecule in pharmacy. Let's break it down. In a covalent bond, electrons aren't always shared equally. Think of it like a tug of war. If one atom is stronger, more electronegative, it pulls the electron cloud toward itself. This permanent displacement of sigma electrons along a carbon chain is the inductive effect. It only travels through sigma bonds. It weakens as distance increases, usually vanishes after 3 carbons. It is a permanent effect. Now, let's answer our big question. Why is acetic acid stronger than ethanol? In ethanol, the methyl group has a positive inductive effect. It pushes electrons toward the oxygen, making the OH bond stronger. Oxygen doesn't want to let go of the hydrogen. In acetic acid, we have a carbonyl group. This oxygen is very greedy for electrons due to negative inductive effect. It pulls electrons away from the OH bond, making it weak and polarized. Conclusion: in acetic acid, because the bond is weak, the hydrogen pops off easily. That's why it's a stronger acid. With negative inductive groups, if you attach a chlorine to the alpha carbon, it pulls even more electrons away from the carbonyl carbon. This makes the carbon starving for electrons, making it highly reactive toward nucleophiles in. With positive inductive groups like in ketones, you have 2 alkyl groups pushing electrons toward the carbonyl carbon. This feeds the positive charge, making it less hungry, and therefore less reactive than an aldehyde. In case of reactivity of alkyl halides, how acidity and reactivity related to inductive effect and acidity. Acidity is essentially a measure of how easily a molecule can donate a proton, H+. For a molecule, HA, to be a strong acid, 2 things must happen. The hydrogen in molecule bond must be weakened. The resulting conjugate base, A-, must be stable. The negative inductive groups are acidity boosters. Groups like Cl, number 2, fluorine and Cn pull electrons away from the acidic site. Bond weakening. They pull electrons toward themselves, making the OH bond more polar and easier to break. Stabilizing the anion. Once the H+ leaves, the remaining oxygen has a negative charge. Negative inductive groups suck that negative charge toward themselves, spreading it out. In chemistry, dispersed charge equals stability. Rule: higher negative inductive effect equals higher acidity equals lower pKa. The positive inductive groups are acidity suppressors. Alkyl groups like CH3 or C2H5 push electrons toward the acidic site. By pushing electrons toward the OH bond, they make it less polar and harder to break. Destabilizing the anion. After the hydrogen is gone, the positive inductive group keeps pushing electrons toward the already negative oxygen. This crowds the charge, making the molecule unstable. Rule: higher positive inductive effect equals lower acidity equals higher pKa. Let's see how inductive effect affect reactivity. Reactivity depends on how hungry or rich a specific atom is for electrons. The inductive effect determines the electrophilicity or nucleophilicity of a center. For example, the reactivity of carbonyl compounds. In aldehydes and ketones, the carbon is partially positive delta plus because oxygen pulls electrons away. The inductive effect dictates how easily the X or leaving group can depart. In S_N1 reactions, the stability of the carbocation intermediate is key. Tertiary carbocations are the most reactive because they have 3 positive inductive alkyl groups pushing electrons to stabilize the positive charge. In GPAT, you'll often see questions like, which is more acidic? Remember, negative inductive groups increase acidity. If I add 3 chlorines to acetic acid to make trichloroacetic acid, those 3 pullers make the acid thousands of times stronger. In pharmacy, this helps us understand how drugs like aspirin, acetyl salicylic acid, behave in our stomach. Let's compare how inductive effect determines the potency of ciprofloxacin and aspirin. To understand drug potency, we have to look at how easily a molecule can react. Take aspirin. Its primary job depends on its acidity. In the structure, we have an electronegative ester group sitting right next to the carboxylic acid. This ester group acts as a powerful electron withdrawing group. It pulls electron density away from the OH bond. This weakens the bond, making it much easier for the hydrogen to leave as a proton. This high acidity is what allows aspirin to inhibit the COX enzymes, stopping pain and inflammation in its tracks. Now, let's look at the heavy hitter, Ciprofloxacin. This is a fluoroquinolone antibiotic. Its secret weapon? That single fluorine atom at the C6 position. Fluorine is the most electronegative element in the periodic table, making it a supreme puller. By pulling electrons toward itself, fluorine changes the electronic environment of the entire ring system. This inductive effect increases the drug's lipophilicity, its ability to dissolve in fats, allowing it to penetrate bacterial cell walls with incredible efficiency. Without that effect, the drug wouldn't reach its target, and its potency would plummet. In our next video we will learn resonance and mesomeric effect, plus M. Don't miss it, subscribe and hit the bell icon. Happy learning. Thank you.